I'm a lead application engineer. I've got about 17 years of Atoms experience. I first got my start using Atoms as a senior application engineer, or excuse me, a senior NVH engineer at Bosch Braking Systems. And so I used Atoms to solve a lot of NVH problems. I have a lot of fun using Atoms, and it solves a lot of interesting problems. And I currently live in Austin, Texas, which is an interesting place to be today since it's St. Patrick's Day and South by Southwest is going on. So I definitely want to avoid downtown Austin today. So it's a good day to be doing a webinar. So with that, I want to go ahead and give you a little bit of background on what we're going to do here today. I'm going to set up the problem for you, kind of give you a brief description of this problem of developing load stroke curves, including an example of how we're going to solve this problem in Atoms. And then I'll give you a demo using an aircraft control surface. It's the flap model that you see on your screen. Hopefully the animation comes through. Try that again. And then after the demo, which will include a review of some results, I'll give you some considerations to take into account when you're modeling flex bodies, and then where to get some more information, and then we'll, of course, have a Q&A session at the end. So with that, let's go ahead and continue on. So this problem of developing load stroke curves is something we encounter with things like landing gear design and flight controls. It's a really familiar problem. We need to understand how the load on an actuator is going to vary with position. Sometimes our motivation for this is that we need to understand just the straight-up load stuff for stress analysis on components. Other times we're designing a control system, and we want to know something about the kinds of loads we're going to encounter when we're designing that control system. Now, one of the things that I've talked to many different people in various aviation companies, and a lot of them use FE solvers to get this information. And the problem with doing this with an FE solver is that it's very time-consuming because they have to manually adjust the model at each time step or at each position and then rerun the analysis. And then the other problem is that if they're using a static load, say they apply a static load with some factor of safety that they've assumed, then the results may not be accurate. And as engineers, of course, we hate to under-design something because failure is not an option. So we tend to over-design stuff. And, of course, then we don't have an optimized system for whatever it is we're doing. Atoms can solve this problem in one pass. And while we're doing that, we're also generating the dynamic loads that we need for use in more detailed FE analysis. And, of course, because we've got these dynamic loads, our FE analysis will be more accurate. So let's talk a little bit about how we're going to solve this problem in Atoms. First, we're going to create a flexible body directly from a modal neutral file. Now, for those of you familiar with Atoms, you're probably familiar with our crawl, walk, run approach. And in that, we don't generally recommend creating a flexible body directly. However, sometimes it's necessary, and I'm going to illustrate how to do that today. It's very straightforward. What you'd want to do as part of that is actually make that flex body rigid and run that analysis with the rigidized flex body just to make sure that you don't have any issues that you need to debug before you go to the full flex body analysis. And then continuing on, we're going to use a command file to automate constraint creation. A little caveat to this is that using command files is a great way to add complexity to a model without having to basically interact a lot with the model. This works really well if you have a standard naming convention in your company, because the command file is going to use whatever names that you've assigned to it. So if you have a standard naming convention for components, this is a great way to automate some constraint creation in the model. Next, we're going to apply a simulated aerodynamic load to the flexible aircraft control surface. This is going to be a simplified method. There's several different ways of doing this. I'm going to show you a very simplified method that's just for illustrative purposes. In reality, you probably want to either use a user subroutine or maybe a co-simulation with the CFD code. And we have examples of how to do that in the Sim Companion and in some of the documentation. Then we're going to run a simulation and create a plot showing actuator load as a function of displacement. And just to let you know, this is the classic will it work scenario. So if some of you have seen my slide here on why do we build an atoms model, this is what 60% of the people who use atoms are using atoms for. So 60% of the cases, it's just verifying motion performance and determining will it work. Now the beauty of this is that using the same model, we could continue on with computing detailed loads in this mechanism, and we really wouldn't have to do any extra work for that. So now I'm going to go ahead and kill the PowerPoint presentation. We're going to go straight into the aircraft control surface demo. So you should see my Atom screen up here now. And as you can see, we've got some aircraft controls here, but no surface yet. So if I look over here at the model tree, I've got my components listed here. And what we're going to be looking at today is actually this inside drive eye. It's the highlighted component here. There are actually some joint motions assigned here. So we're going to use the joint motion as our measure of displacement. And there will be another constraint on this inside drive eye that we'll use for loading. This is going to be a universal joint here. I'm going to take just one component of that to illustrate the loading conditions here as a function of displacement. So with that, let's go ahead and create our flexible body. So in order to do that, we're just going to import a modal neutral file. I'm not going to change the name of it because, again, my command file depends on having a standard naming convention here. So I'm going to browse over here to get my modal neutral file. And I'm just going to leave everything else as a default and click OK. And now I have a modal neutral file here. So now what I need are constraints, because I've got my rigid constraints set up here. I need to change this so that I've got some flex body constraints. And I'm going to turn on my icons now so you can see where everything is. So in order to create my constraints, I'm just going to import a command file. I'm going to browse over to that. It's just the create joints one. And when I do that, now I have created some additional constraints here. So you can see that there are actually universal joints created on there now, where there weren't before. So let's continue on here. One of the things I'd like to show you really quick is let's go up here and do a model verify. So now we have a constrained model with a flex body included in it. And so what it tells us is we've got 80 degrees of freedom, no redundant constraints. So we verified the model successfully. Now, what I'm going to do here is I'm going to modify this flex body. With a flex body formulation, you have our inertia model, and you have several options here. Partial coupling is the default option, but if I select rigid body, then I can make this flex body behave as a rigid body. So that's what I'm going to do right now. And then if I go back up here and I do model verify again, up here we had 80 degrees of freedom and no redundant constraints. If I come down here now, I have 0 degrees of freedom. So technically a kinematic model, but I also have 2 redundant constraint equations. Now, this would be a problem here if I wanted to recover loads from those locations, because what happens when you have redundant constraints is that the atom solver will deactivate the redundant constraints. And when it deactivates a constraint, you don't get load case information from that constraint. So this is something to pay attention to if you want to recover loads from your atoms model. So it's just an example of what happens when you change something from rigid to flex. I'll go back to partial coupling here. And while I'm at it, I'll go ahead and show you. You can animate the modes here. So I've got some modes here that I can continue on showing the different modes and animations here. Okay. So Atoms uses the modal superposition method for modeling flexibility. So you have all those modes in there. If you discover that you don't need certain modes, it is possible to go in there and deactivate them. So now that we've done a little bit of comparison between rigid and flex, the next thing we need to do is add some loads to our control surface. So in order to do that, I'm going to change my appearance of my flexible body a little bit. I'm going to make it a little bit transparent so I can actually see some markers in there, because I want to apply some loads at these markers. What I'm going to do is go over here to my Forces tab, and I'm going to select a single component force. I'm going to leave it as space fixed. I'm going to pick a feature, and I'm going to make it a custom load. So let me go in here and find I'm going to pick the flex body, and then I'm going to select this node. And I actually have a marker on this node, so I'm looking for, the Z component. There we go. So now I've created a single component force that's applied to a marker at that node. And now what I want to do is use a function to define this aerodynamic load. And again, this is not an accurate aerodynamic load. I'm only doing this for illustration purposes, but I'm just going to use a step function in here. Take that space out. So this step function is going to ramp up the load from a load of 0 at time equals 0. It'll smoothly ramp it up to 1500 at 1 second, or minus 1500 in this case. So click OK and apply that. Now I want to create one more. So we're going to do the same thing. I'll do custom again. All right. So again, we'll select the flex body. I'm going to select another node this time. There we go. And again, I will paste the same function in and apply the load. So now we have aerodynamic loads applied, simulated aerodynamic loads. We have a flex body. We have all of our connections. And now we are ready to run a simulation. And I have a simple scripted simulation set up. So there's a simulation script, and let me show you what that looks like. Very simple script that says run a static simulation, and from then go into a dynamic simulation for 3 seconds, take 180 steps, and then stop. So very simple simulation here. Let me pull this out of the way, and we're going to run it in real time here. I'm going to get some warnings here. I can ignore those. It has to do with some splines that Adams doesn't like, and they actually don't affect the simulation. So now we've run our simulation, and from here we can go over and we could actually save the simulation results right here. So if we want to do that, I can save the run results and just say flex if I want to, and auto increment the name. Okay, so I could save that there. I'm not going to save those right now. Let's just go over to results and have a look at what we have here. Now, one of the things I'd like to do is plot that S-force, the single component force, just to make sure it's doing what I think it's doing. And in fact, it is. So this is the simulated aerodynamic force that I created. So that's doing what I expected it to do. The next thing, let's go ahead and plot the results of this constraint versus time. So let me look at what I'm looking at is the inside eye to flap constraint. Let's look at the element force, and I would like to take a look at the Z component. So I see what's happening to this as a function of time. But remember, in order to get our load stroke curve, we need this as a function of displacement. So let's create one more plot. And for this plot, I'm going to look at joint motion 2 actually contains the displacement. So I'm going to just use Z. And actually, I want to change this here. So it's actually a constraint. Come over to joint motion 2, translational displacement, Z. That now becomes my independent axis on the bottom. And now all I have to do is come back up, find my universal joint eye to flap, element force Z, add the curves. And now we have displacement, or the force versus displacement for that actuator at that location. I could also plot the other components of the force there. So if I were creating some detailed load information about that location, I could actually put some additional information on there. So for example, add the Y component. Let's see, that's the X component and the Y component. The Y component is very small, so if I wanted to not look at that, I can just undo it. So that's a very simple way of creating a load stroke curve using atoms. And with that, I'm going to, I think, leave the demonstration here. Go back now. The other thing we'd want to do is rerun this using a rigid case. And if we rerun it with the rigid case, then we're going to get very different results. I've actually got some of those results that I'd like to show you here. So in this case, you remember we saw this. This was the flex case that we just reviewed. I reran it using the rigidized flap, and this is what I got. So here's an example of how including flexible bodies can make a big difference. There are basically two reasons to put a flex body in a component. One of them is that you think the system is going to do something to that component that will deform it under load. In fact, we would expect that the system would, a flap would deform under load. The other thing is that you think that the flexibility of a component will have some impact on the performance of the system. And in this case, the flexibility of the flap, of course, affects the performance of the system. So in this case, we have two reasons to include a flexible body. Now, there are some considerations to take into account when we're using flex bodies. So one of these is we, of course, create a modal neutral file using an FE program, or you can use Atoms Flex if you prefer. This modal neutral file is going to relate the finite element model to the geometry, and it contains things like geometry, including location of nodes and connectivity, nodal mass and inertia, mode shapes, and then the generalized mass and stiffness for the mode shapes. One of the things to think about is that you might want to identify the attachment points in the rigid body and put a node there. One of the reasons to do that is that when you bring in your modal neutral file and you're connecting it up to the constraints in your atoms model, Atoms Flex is going to take a look at where the nearest node is, and it's going to basically put a marker there to connect your constraint to that. Sometimes if the marker is too far away, you could end up with a pretty large moment, depending on how you're connecting stuff up. And so you might just want to put a node there so you make sure that you have your constraint marker right in the exact location where you want it. One of the things to do when you're creating your FE model is avoid using constraints. So constraining your model in your constraining your FE model when you're creating your modal neutral file can cause some inaccurate results because those constrained nodes are never going to move relative to other nodes. So there is an exception. So if you have a component that's fixed to ground at a particular location, then it might be appropriate to put a constraint in your FE model. The other thing is that if you know that a particular node is never going to have motion in a certain direction, you may constrain that particular node in that direction. But just be very careful. If you always run a free analysis when creating your FE model, you're probably not going to go wrong. So the other thing is when you're applying forces to a flex body, the flex body cannot be the reaction body. So make sure that if you're using forces in there, that you pay attention to that because that will cause some problems for you. So what if you need some more information on this, if you're curious about how to do this? The Atoms documentation is a great place to start. There are some examples in the Getting Started parts of that using Atoms Flex. The Adams Flex documentation has some examples as well, and Viewflex documentation describes how to use Adams Viewflex to create your flex bodies inside Adams. In addition, there's a theory of flexible bodies that explains the whole modal superposition method and how Adams handles flexible bodies. That's useful information to have when you're creating flex bodies. In addition, if you're using nonlinear flex bodies, there's a couple of ways of doing that. Historically, we've had to use the discretization method where you've had discrete flexible links connected with either fixed joints or compliant connectors. Now we have the ability to create nonlinear flex bodies using the Adams FE part capability. That's included in the documentation as well. And if you want more information on automating and customizing Adams, there's a Sim Academy webinar on file. It's called Gaining Efficiency Using Adams View Scripting Logic and Macros. That's worth checking out. And Sim Companion has a lot of information on how to use scripting and macros and command files for enhancing your models. So with that, I'll open it up to questions. I hope this was some good information for you.